Now we want to take a look at the graph of the logarithmic function. And we actually want to think about how the graph of the logarithm compares to the graph of the exponential with the same base. So first, let's go ahead and plot some points to graph this function. So plug in some values for x, get out some values for f of x. Okay, and then remember that f of x equals log base 2 of x. So since we're playing this like what's your exponent game, we want to think of easy, friendly numbers to plug in. So 2 to what power gives us the number that we're plugging in. So maybe if we start with the value 1, log base 2 of 1 is like asking 2 to what power equals 1. So the power would have to be 0, because anything to the 0 power is 1. All right, now let's plug in another power of 2. So let's say log base 2 of 2. Again, that's like asking 2 to what power equals 2. So that power, the exponent, would have to be the number 1. So if we plug in 2, we get out 1. Let's plug in another power of 2. Say log base 2 of 4, say. This is like asking 2 to the what power is 4. So that power would have to be 2. So plug in 4, get out 2. Let's just do one more. Log base 2 of 8 is like asking 2 to what power equals 8. That power, the exponent, would have to be 3. So plug in 8, we get out 3. Let's go ahead and plot these values. 1, 0, 2, 1, 4, 2, 6, 7, 8, 3. All right, now let's see if we can plug in. I don't want to plug in any negative numbers because 2 to no power would give you something negative. But let me plug in another power of 2, say 1/2. So log base 2 of 1/2, that's like asking 2 to what power is a half. So that power would have to be -1. So if you plug in a half, you get out -1. So that's like right here. Another power of 2 that we could plug in is 1/4. Log base 2 of 1/4 is like asking 2 to what power is a 4th. That power would have to be -2. So at 1/4, we'll get out -2. And what you should see is when I plug in values like a half, a 4th, 1/8, 1/16, values are getting closer and closer to 0. The outputs that I'm getting are going to be closer, like they're going to get really big and negative. So basically what I'm saying is that the graph of this logarithm function is going to look like so. What we're going to see is that we have a vertical asymptote right at x equals 0. So we have a vertical asymptote, x equals 0. And then we have a couple key points. The key points are when the input value is equal to 1, when the input value is equal to the base, and then we could say either when the input value is 1 over the base, or even when the input value is some power of the base. So 3 key values. And I want us to also notice how this relates to the graph of 2 to the x. And remember, the graph of 2 to the x, we're going to have a horizontal asymptote, y equals 0. And some points that we could plug in, well, when x is 0, y is 1, when x is 1, 2 to the first power is 2. When x is 2, 2 squared is 4. So 2, 1, 2, 3, 4. And when x is 3, 2 to the third power is 8. So plug in 3, we get out 1, 2, 3, 4, 5, 6, 7, 8. And then when you plug in negative values for x, like 2 to the negative 1 power is a half. 2 to the negative 2 is a fourth. 2 to the negative 3 is an eighth. And we just get really, really close to this horizontal asymptote here. Okay, so I want you to notice that these two graphs are very similar to each other. And in fact, they are reflections of one another about the line y equals x. So if I draw in the line y equals x here, what I want you to see is that this line y equals x is like a line of symmetry between these two graphs. And this has to do with, if you remember when we covered inverse functions, the way to create inverse functions is to flip-flop the x and the y. Here's our x-axis, here's our y-axis, and then solve for y, and that will help you to compute the inverse function. So if we flip-flop the x and the y, the logarithm graph becomes the exponential graph and vice versa. Also to notice, exponential graphs have horizontal asymptotes. Logarithm graphs have vertical asymptotes. So they're very related to each other. All right, let's do another. Oh, and we should also notice that since our base, the base 2 is bigger than 1, what we have here is logarithmic growth. Just like with exponentials, if the base of the exponential was bigger than 1, you had exponential growth. Exponential growth is like, those are values that grow very, very quickly. Values that grow logarithmically actually grow really, really slowly, okay? Which also has to do with the fact that these guys are inverses of each other. All right, let's look at one more graph where the base of the function is a number less than 1. So again, what I want to do is plot some points. I should expect to see, oh, this is g of x. I should expect to see a vertical asymptote somewhere. And notice that there's certain values that you cannot plug in for x. Like if I tried to plug in -1, what would happen? If I did log base a half of -1, that's like asking 1/2 to what power gives me -1. There's no exponent that would make this equal to a negative. So that's not possible. And if you try to plug this into your calculator, you get an error message out, okay? So we're not allowed to plug negative numbers into the logarithm function. Similarly, we can't plug in the number 0. Log a half of 0 is like asking 1/2 to what power gives us 0. There is no such exponent where you multiply a half times itself so many times that you get out 0. So here you'd also have an error message if you tried to plug it into your calculator. So moral of the story is that the domain of these logarithm functions are going to be all positive numbers from 0 to infinity, not including 0. Okay, so let's go ahead and plug in some numbers. Plugging in 1 is like asking 1/2 to what power is equal to 1. The power would have to be 0. So 1, 0 is a point on our graph. Let's plug in a power of a half so that it'll be easy for us to compute. Say 1/2 to what power gives us a half? That power would have to be 1. So if I plug in a half, I get out the number 1. So plug in a half, you get out 1. Let's plug in a fourth. 1/2 to what power is a fourth? That power would have to be 2, right? So plug in a fourth, you get out 2. Okay, now let's start plugging in the reciprocals. Like 1/2 to what power equals 2. So if I plug in the value 2, the exponent would have to be -1. It'll be right there. Let's plug in another reciprocal power of 2, the value 4. 1/2 to what power equals 4? That power would have to be -2. There we go. And one last. 1/2 to what power would give us 8? That power would have to be -3. So if I plug in 8, 1, 2, 3, 4, 5, 6, 7, 8, we get out 1, 2, 3. Alright, so our graph is going to have a vertical asymptote, and it will be decaying. And here's our vertical asymptote. I'll draw it in with a dashed line. And maybe I'll indicate it here. X equals 0 is the vertical asymptote. And notice that this is logarithmic decay. Opposite of logarithmic growth. All right.